So this video is an optional video. I'm going to show you how you can get Bessel's equation through Laplace transforms, which is not the usual way that it's done. It's usually done with power series. But I think the Laplace method is sort of slick. And it also shows a thing that you often don't see when you study Laplace transforms, which is how to deal with the situation when you end up with a differential equation in the transform variable. So here we've got non-constant coefficients, right? So there's r's here and here. And those r's, the rule for them is that just like derivatives in the x domain transform into powers of s in the s domain, it works the other way around as well. So powers of x turn into derivatives in s. Or in our scenario, powers of r turn into derivatives. And those derivatives come with a minus sign just because the way Laplace transform works. So when we take the Laplace transform here, that r is going to become a minus dds, and our y double prime is going to be s squared y minus as minus b. Oh, and I should point out here, I'm treating it like it's an initial value problem, so I've got an a and a b as the values of y0 and y prime 0, but you'll see that it doesn't really matter in the long run. So, okay, and then we've got the y prime term. So the y prime term transforms to sy minus a. And then we've got lambda times, and then the r becomes minus dds. And then that's going to be applied to just y. And then this is equal to 0. Okay. So now we've got some differentiation to do, and this is going to take product rule here. So this is going to be 2sy plus s squared y prime. And when we collect up all the bits and pieces, what happens is the a's and b's go away. So this b is going to get differentiated into dust. This one here is going to become a positive a because the negative sign and the derivative. And over here we have a minus a, so the positive a and the negative a, those ones cancel with each other as well. So long story short, we end up with y prime plus s over s squared plus lambda y equals 0. And so this equation is linear, it's separable, you can solve it however you like. And you end up with y equal to c, some constant, over the square root of s squared plus lambda. And so this does not look like a fun thing to try and invert the Laplace transform on, but you can actually manhandle it a little bit. So if we pull a factor of s out of the denominator, we can rewrite this as 1 plus lambda over s squared to the minus 1/2. And the reason why that's useful is because we can then use the binomial series, everybody's favorite, the binomial series. It's probably that one that you immediately tried to forget after passing Calc 3 because it's so crazy looking. But it's super useful. So for the coefficient, we have minus 1/2, minus 3/2, minus 5/2, and so forth. And these in general look like 1/2 minus, minus n. And this is all over n factorial. And then the thing on the right-hand side of the binomial expression right here is the thing that's being raised to the nth power. So we have that, the binomial series. Okay, and so now we can go to town. Let's see. So we've got c over s summation. I'm going to collect the minus 1 from each of those powers and count up the number of powers I've written there. There's n of them. That also means that if I collect all the halves and put them in the denominator, then there's going to be n of them down there with n factorial. And then what's left behind? Well, 1 times 3 times 5 times up to, and then if you work it out, it's 2n minus 1 is the top odd number appearing in the numerator. And then we've got lambda to the n over s to the 2n. And to make some kind of sense out of this, I'm going to give the factorial in the numerator what it needs. So the idea is that this expression wants to be the factorial of 2n, but it's missing all the even terms, right? So it's missing 2, and it's missing 4, and it's missing 6, and so forth, all the way up to 2n, right? So I'm going to have to divide by all those as well. And so now if I look inside all these factors that I've just added, I have a 2, 2, 2. How many 2's do I have? I have n of them. And I have a 1, 2, 3, up to n all multiplied together. So I have an n factorial. So long story short, this expression here inside the green parentheses is equal to 1. So I'm okay multiplying that one in. So let's see. So now I can combine these things, and I'm going to put that s inside, so I'll just leave c out front. I have -1 to the n, and then on top I have lambda n 2 to the 2n, because I'm now combining those two, and n factorial squared, because I now have two n factorials. And then I have s to the 2n plus the one that used to live out in front of the summation sign, all over 2n factorial. And this guy here exactly fits the form for t to the 2n on the Laplace transform table. So I can transform this back, assuming that term by term Laplace transformation is valid for this infinite series, which, gee golly gosh, it turns out to be. So we have this, then I have lambda to the n, 2 to the 2n, n factorial squared, t to the 2n. So if I want to combine those terms, I can make this a square root raised to the power 2n. And then this is exactly c times j naught of t root lambda. And to find out what the value of c is here, you can see that this series right here has these powers of t in it, and when I evaluate t equal to 0, the only one that survives is the 0th term. And for the 0th term, all the rest of this nonsense evaluates to 1. And so that leaves me with a y of 0 on the left-hand side, or j naught of 0, same thing. And on the right-hand side, a c. So sorry, I miswrote that here. Whoops. This should have been here. And then we have whatever we're given as our initial value right there. Okay, so if I take my initial value a equal to 1, then c just equals 1. Actually, yeah, why am I even... well, okay. That looks strange. Let me just point out that this guy here is equal to 1. All right, fair enough. So that's good enough for whatever you need to do with the Bessel function for this problem.